In this video, we're going to focus on another application of differentials, which is error propagation. This has something to do with errors in measurement or errors in measuring quantities. It can be quantities involving geometric figures like radius, height of a cylinder, so on and so forth. And then because we are dealing mostly with geometric figures, it means we will be using some geometric formulas like area formula, volume formula, surface area formula, so on and so forth. So for instance, we have a general formula. For now, let's just use a general function, all right, in this form y equals f of x, where y depends on the value of x. Think of, for example, area formula for the circle. So that's a equals pi r squared, where a depends on the value of r. The same way as y depends on the value of x in this case. If there's a change in x, then there's a corresponding change in y. Okay, we did this with the approximation formula, right? If you can still remember. So this becomes y plus delta y equals f of x plus delta x. Then again, the same with the approximation formula. If the changes are very, very small, then we can rewrite this equation as y plus dy equals f of x plus dx. Okay, so for problems that involve errors in measurement, we can use dx, or the differential of x, to describe the error in the measurement of x. All right, this means it can be an increase or decrease in the value of x. Okay, and the same way, we can treat, or we can use the differential of y to describe the error in the quantity of y. Okay, again, it can be an increase or decrease in y. All right. We are also interested in the approximate relative error in the quantity of y, or any other quantity. It can be of x or any other uh, quantity involved in the problem. So it can be relative error in the radius or the computed volume, so on, so forth. So if we are talking about y, then RE is dy over y. And then the approximate percentage error is just dy over y times 100%. Okay, so again, this can be any other quantity. It can be in terms of x, it can be in terms of radius of the circle, or height of a cylinder, or radius of a sphere, so on, so forth. Okay, so let's look at some examples. First problem, we have here the radius of a circle is measured to be 15 centimeters. If the measurement of the radius is correct to within 0.1 centimeters, this means that the radius has an error in its measurement, so it ranges from 14.9 to 15.1. Okay, because it is said here that it is correct to within 0.1 centimeters. So we are asked to find the approximate propagated error in the area. Okay, so let's identify the given first. We have the measured radius, which is 15 centimeters, and the error in measuring the radius, which is within 0.1 centimeters. So that's positive, negative, or plus minus 0.1 centimeters. All right. dr, again, this represents the differential of the radius. This represents the error in the measurement of the radius. All right. So required, since we are asked to find the approximate propagated error in the area, this is represented as dA. Okay, differential of the area. The error which results from the error in measuring the radius. Okay, so solution, let's start with the area formula for a circle. So that's pi r squared, and then take the differential of the area. So we have here 2 pi r times dr. Okay, this is now our working equation for the required, which is dA. All right, so just substitute or plug in the values for r and dr to get dA. All right, So R is 15, dr is plus minus, or positive negative zero point 0.1. Therefore, the approximate propagated error in the area is positive negative 3 pi square centimeters. Or this is approximately equal to positive negative 9.42 square centimeters. This means that the computed area that we can obtain here is correct to within 9.42 square centimeters. All right. Next problem. The radius of a sphere is measured to be 4 inches with an error of 0.002 inches. So it's the same with the previous problem. We have a measurement for a quantity, in this case the radius, and it's correct to within a certain value, in this case 0.002 inches, which also uh, represents the error in the measurement. We are asked to find the relative error in the computed volume. Okay, so given we have the radius, let's call the radius of the sphere as capital R, and it's equal to 4 inches. And then the error in the measurement of the radius, it's dr, right? And it's equal to plus minus or positive negative 0.002 inches, or positive negative 1 over 500 inches. All right. Required in this case is the relative error. So it's the ratio between the error in the computed volume and the measured volume. So that's dV over V. Okay. So let's start with the volume of volume formula of a sphere. That's 4/3 pi r cubed. And taking the differential of V, that's dV. So this will result to 4 pi r squared times dr. Okay. Then we can immediately proceed to uh, the formula for the relative error, which is dV over V in this case. Okay. So dV over V, plug in the equivalent expressions for dV and V. We have 4 pi r squared dr divided by 4/3 pi r cubed, and just uh, cancel out the common factors. Okay, so this will give us 3 dr over r, and just plug in the values for dr and r. For dr, we can just exclude positive or negative, okay, because we're computing for the relative error. So just put 1 over 500 for dr, then divided by 4. This will give us 3 over 2000, or that's 0.0015. This is now our relative error, or this is the relative error in the computed volume, which results from the error in the measurement of the radius. Okay. Next problem. If an error of 1.5% is made in measuring the side of an equilateral triangle, find the percentage error made in the computed area. So what we are given here is a percentage error in the measurement of the side of an equilateral triangle. So we can call that ds over s times 100%. Okay, this is the formula, right, of percentage error. In this case, in terms of the side of an equilateral triangle. Okay, so that's 1.5%. It's the only given, and then we are required to find the percentage error, in this case, in the computed area. So dA over A times 100%. All right. So let's start with the area formula for equilateral triangles involving the side. Okay. So area formula in this case is A equals square root of 3 over 4 S squared. S pertains to the side of the equilateral triangle. Okay. And then taking a differential of A, this will give us square root of 3 over 2s times ds. Alright, so formula for the percentage error in the computed area, that's dA over A, 100%. So substitute, dA is square root of 3 over 2s ds, and then A is square root of 3 over 4s squared. cancel out the common factor so that we can simplify. And then this will give us 2 times ds over s times 100%. Okay, so in this case, there's no need to determine the actual value for s and a ds, right? Because as you can see, this expression here, ds over s, is actually, or ds over s times 100% is actually the given percentage error in measuring the side of the equilateral triangle, right? So 1.5%. Just directly plug in the value. So 2 times 1.5%. Therefore, the percentage error made in the computed area is 3%. Okay? This is the result in the error in measuring the side of the equilateral triangle. All right?